Welcome to Calculus 1. In this lecture video, we're going to talk about more integrations by this technique called the U substitution. Okay, integration by the technique called the U substitution. Okay, so this is how it works. Okay, so this is really for more complicated functions. Okay, just like using our chain rule for derivative. So let's say we have a function g, okay, whose range is in the interval I. Then let function f, okay, to be continuous on the interval I as well. So if this function g is differentiable on its domain, and the calculator f, the antiderivative, okay, is calculator f is the antiderivative of the function lowercase f, then the integral of the composite function, okay, times g prime of x will equal to the antiderivative of the function g of x plus c. So it will just equal to the antiderivative, and inside the antiderivative function you have the function g inside of it. Okay, so this is designed to be used for composite functions. So if we do it differently, if we do it from the U substitution perspective, we can say let U equal to this inside function g of x, okay, du will become g prime of x dx. So that means this entire g prime x d sub x will become du, derivative in respect to u. Okay, and then this g sub x will replace it with f of u instead. Okay, so that's called the U substitution. I'm using another variable, okay, to represent part of my function, or representing the composite part of the function. Okay, so let me show you how this works. Okay, this is this requires a little bit of pattern recognition as well. What do you set u equal to? Okay, what are you gonna use to substitute? What is substitute for u? So that all depends on how the function look. Okay, so I'm gonna show y'all the technique here for a minute. So this requires a little bit of thinking ahead of time. Okay, I want my function end up to be looking like fu times d sub u, so I can take an integral of it very quickly and make it simpler, okay, to do the integration. So if you notice this part of the function, if I let my u to become x squared plus 1, okay, and I'm going to take a derivative of this x squared plus 1, that will actually equal to 2x. So that will cover up this part of my function. So if I let my u equal to x squared plus 1, and I'm going to take a derivative, okay, on both sides, so that's going to be du, and this part going to be 2x dx, okay, using an implicit differentiation. So now this 2x dx will actually be this part right here, replacing with the du. So u is x squared plus 1, so I'm basically trying to take an integral of u squared and then du, derivative in respect to u. So that's the pattern we need to recognize when we use U substitution. Because if I will take a direct integration of this function, how am I going to deal with the square part? Okay, how does the square part work, and how does these guys inside of the parentheses is going to turn out to be. So we are basically using chain rule backwards in a sense, okay, but we are actually substituting with other, we're actually substituting part of a function with another variable to simplify the entire process. Alright, move the exponent down, so that will be 1 over 3 u to the third power plus c. Now I'm gonna replace the u back to what I set them equal to from the beginning. So that means this answer will be 1/3 times x squared plus 1 to the third power, then plus c. Okay, so that's the answer. Now let's try another one. Alright, integral of 5 times e to the 5x. So, in this case, I gotta think ahead of time. If I let my u equal to e to the 5x, alright, and I'm gonna take a derivative on both sides. So one side, this is 1u, so that'll just be d sub u. So that du will equal to, alright, derivative of e to the 5x. So as you can recall, derivative in respect to x, e to the u will be eu times u prime. So for us, that will be e to the 5x times u prime, and my u here is like the 5x, so that would just be 5. So I'm going to put that 5 in the front, dx. So it turns out this entire thing is the same as this. Okay, so what I'm taking integral of is basically just 1 du. Alright, so when I take an integral of a constant, I will just put the variable back on plus c. That's why my final answer will just be e to the 5x plus c. Okay, so this 5 from the prob, this 5 actually is the same 5 as with the dx. Okay, so that means this whole part becomes just a d sub u, which is 1 du. And that constant 1, when I take integral of it, I just put the I just times by the variable that I'm integrate with, which is u. Alright, so it's not too hard once you recognize the pattern here. Now let's try this one. I'm gonna let, with the square root of 2x minus 1, I'm gonna let u equal to this. Okay, let's see how it's gonna turn out. So u equal to 2x minus 1. Okay, this is dx. I need it to become du, so I take a derivative on both sides. So du is equal to 2x. Excuse me, just 2 dx. Alright, so this thing here in the problem is just dx alone. So if I get dx by itself, that will just be du over 2. So if I write it out, okay, that will be square root of u times du over 2, because I'm replacing dx with du over 2. Alright, this half can be pulled out to the front of the integration sign. Alright, square root of u is u to the half power, and I put this half to the outside, that'll just give me du here. Alright, so that will be half times 1 over, bring the exponent down, plus 1, u to the half plus 1 plus c. So half plus 1 is 3 half. 3 half Oops. One divided by 3/2 is 2/3. So the 2 cancels out, so that leave me with 1/3 u to the 3/2 power plus c. And then I'll bring my u back, so that will be 1/3 times 2x minus 1 to the 3/2 power plus c. Okay. Alright. Now this one look just like the one we've done, okay, except there's an x times in the front of it. So again, I'm going to let my u equal to the 2x minus 1 here. Okay, this is a lot of manipulation. Alright, now, if I do a du, if I take a derivative on both sides, that will still be 2 times dx. And to get dx by itself, I will divide both sides by 2, so my dx will become du over 2. Alright, so that does not answer the question of what about this x, because when I take an integration in respect to u, this x cannot be there. So what will I have to end up doing is solve for this x. I want this x to turn out to become represent some type of u. So back to the u equal to x minus 1. If I'm trying to get x by itself, I can move the negative 1 over. So that will give me u plus 1 equal to 2x. And to get x by itself, I divide both sides by 2. So that gives me u plus 1 over 2. So I will replace x. I'll replace x with this. Okay. I will replace my u with this. Okay. And dx becomes du over 2. Alright, so if I write it out, this is going to be square root, I believe that, not a square root, I'm sorry, integral of u plus 1 over 2, the x is u plus 1 over 2, times square root of u is u to the half power, times dx becomes du over 2. Okay. Alright, now the 2 and the 2 in the bottom is 4. I'm going to factor that out. So that's 1/4 times integral of u plus 1 will times u half du. Alright, so from here I'm going to distribute my u half onto the 2 terms to kind of split them up. So when I multiply variable, I add my exponent, so that's 1 plus a half, which is 3/2. So I get 1/4 times the integral of u to the 3/2 plus u to the 1/2 du. And I'm going to take the integral separately. So that will be 1/4 times. Alright, bring this one down. I'm going to go ahead and do it here on the side. 1 over 3/2 plus 1. 3/2 plus 1 is 5/2. 1 divided by 5/2 is 2 over 5. U to the 3/2 plus 1 is 5 over 2. Plus, okay, 1/2 come over to the front. 1/2 plus 1 is is 1 over 3 half. 1 divided by 3 half is 2 over 3. U to the 3 half power plus C. Alright, so now I'm going to distribute. So that becomes 2 over 20. Oh, excuse me, not 2 over 20. I'm sorry. I can actually reduce it. That will be 1 over 10. U to the 5 over 2 plus 1 over 6 U to the 3 half plus C. Okay. Now from here, okay, I can actually do what I showed y'all before. I can factor out certain amount of U up front, okay, and factor out a certain fraction up front to make to actually make this thing a little bit, to simplify a little bit better. So between 5 half and 3 half, 3 half is smaller, so I'm going to factor out U to the 3 half. Because what that does is, if I factor out 3 half, there will be U to the 3 half go into U to the 5 half. That means, according to quotient rule, I will subtract. So that will be U to the 5 half minus 3 half is 2 half, which is 1. So that'll just be U. So this one is going to become a U plus this will just be 1. Okay, plus C. Now, what about the 110 and the 1 over 6? Well, a lot of times when I factor out a fraction, what number do I use? That's a very, very tricky question. The point is, whatever I'm going to factor out, what's inside the parenthesis, these numbers in front of the variable need to be a whole number. So we can try it out. If I say, by looking at a 2 fraction here, 110 is smaller. So if I factor out 110, that would just be 1 here, and 110 going to 1 over. See, 110 going to 1 over 6 is basically saying 1 over 6 divided by 110, which is 1 over 6 times what? Times 10 over 1. And in that case, if I reduce them, okay, that would be a 3 and a 5. So that's 5 over 3. So that will make this term 5 over 3. So that's not really ideal, because I want this to be a whole number too. Okay. So this is the part where we can manipulate, and you'll probably see this on the homework saying, how does Mr. Chen come up with that number to factor out? Because that number I factor out will actually turn out working out pretty good for these coefficients. So let's think about it a little bit. If I do the LCD between 10 and 6, okay, if I do the LCD between 10 and 6 using a 2, that's 5 and 3, so that will be 30. So what happens if I factor out 1 over 30? 1 over 10 divided by 1 over 30. So that will be, this is a division sign. So that will be 1 over 10 times 30 over 1. That will cancel out the denominator, and that with a 3. If I take 1 over 6 divided by 1 over 30, means times 30 over 1. That would just be a 5. So if I factor out 1 over 30, okay, that first term will give me a 3. Second term will give me a 5. 1 times 5 is still 5. Alright, so that's why sometimes if you see a problem look like this, an answer look like this way, this is the way how we did it. Alright, so that's 1/30 times u was 2x minus 1 to the 3/2 power times, replace the u with the 2x minus 1, so that will become 3 times 2x minus 1 and then plus 5, so that will be 6x minus 3 plus 5, which will give me 6x minus 2 plus c. So that will be my final answer. There you go. Okay, so if you see an answer look like this on the study guide, that's the reason. This is how we derive it. Now this part E look very complicated, okay, but in reality it is not. Check it out. If you can kind of do your derivative in your head ahead of time, you can see that derivative of x to the third becomes 3x squared, so that will actually become this 3x squared up front. So I'm gonna let my u equal to x to the third minus 2. So du, and the other side is 3x squared dx. The negative 2 drop off when I take a derivative. So now 3x squared dx will be right here and right here. So that so these two factors becomes 1 du. Alright, so I don't have to, I don't have to solve for anything. Okay. So this is going to be the integral of, okay, u to square root of u is u to the half, okay, du. So bring it down. I think we did it up top. Half plus 1 is 3/2. So 1 divided by that is 2/3. U to the 3/2 plus c. And now I will just bring the u back, bring back the u, or bring back the x to the third minus 2. So that'll be 2/3 times x to the third minus 2 to the 3/2 power plus c. Okay, u substitution, very, very powerful technique. Okay, and this is just, and these problems I'm doing are just simple examples, okay, of the u substitutions. All right, take a look at this one. This one is, look, even more complicated. But imagine if I let my u is equal to 1 minus 2x squared, right, what's inside the parenthesis. Then when I take a derivative on both sides, that would be negative 4x. Okay, because 1 drop off, bring it down, dx. So this du part is already covered right here. So that would become, so inside the parentheses a u, so that's 1 over u squared. So this probably becomes 1 over u squared du. Okay. Alright, 1 over u squared is the same as u to the negative 2 power. Alright, so bring my exponent down. This has 1 over negative 2 plus 1. U to the negative 2 plus 1 plus c. So that will give me a negative 1 here in the front, and this is a negative 1 on the top plus c. Alright, bring my, alright, so take the 1 minus 2x squared back for the where the u is, so that'll be negative parenthesis 1 minus 2x squared, okay, to the negative 1 power plus c, and to the negative 1 power, we'll flip it back to the denominator. So my answer, negative 1 over 1 minus 2x squared. Okay, then plus the c. Alright, so if you look at from the original part of this problem to the answer, okay, this is a process we go through. Okay, it doesn't look anything like it So a lot of time when we do integration, you cannot just trying to figure out this answer just by thinking about how can I go from here. Okay, trying to figure out a backdoor way to come up with your answer. We do kind of need to go through the process, okay, to actually figure out how I derive this answer here. All right, let's do same thing, but I'm gonna find do the definite integrals. All right, I'm gonna evaluate from 0 to 1, okay, of this function. So again, this time I'm gonna let my u equal to this inside function x squared plus 1. So if I take a derivative on both sides, I'm gonna leave a little space right here. I get 2x. Alright, so 2x dx. Alright, so you see this x can be used for that x, dx. So this 2 is extra. So I'm gonna divide both sides by 2. Then that would just be x times dx equal to du over 2. So that means x dx here will be du over 2. So this is the integral from 0 to 1 of u is right here in the middle to the third power du over 2. Alright, pull out the half. So that will be half times, alright, bring the exponent down, that will become 3 plus 1 times u to the 4 power, I'm going to say 4 power, evaluate from 0 to 1. So 1/2 times 1/4, 1/8. So it's going to be 1/8 times u is x squared plus 1. I'm going to evaluate it from 0 to 1. Alright, so this is going to be 1 over 8 times 1 squared plus 1. Oh, sorry, to the 4 power, excuse me, to the 4 power right there. 1 plus 1 is 2, 2 to the 4th power, minus 1/8 times 0 squared plus 1, whole thing to the 4 power. So 2 times itself, 4 times is 16. 16 times 1/8 is 2, minus, here just going to become 1/8. So that will be 15 over 8. Okay, that's the area under the curve. Alright. We'll do one more. I'm going to let the u this time equal to 2x minus 1. Alright, so I'm going to leave a little space right here. Okay, so if I take a derivative on both sides, that gives me a 2 dx. So dx alone will be du over 2. I left a little space so we can see that even after I solve for dx here, I still got the x inside my function I need to deal with. So if I solve for x here, that would turn out to be u plus 1 equal to 2x, and x equal to u plus 1 over 2. So imagine I'm replacing this x, okay, with u plus 1 over 2, and down here is square root of u, which is u half, bring out to the top, become u to the negative half, and du over 2, dx become du over 2. Alright, so here I can actually multiply them after I took out the 1/4. Okay, that will work. Or I'm going to show you another technique. Okay, this will work too. Okay. This will work as well. What happens if this time I let my u equal to square roots of 2x minus 1? Alright, in that case, again, I want to deal with that x, so I still need to solve for x. So here I can square both sides. So that's u squared equal to 2x minus 1. Alright, so that will become u squared plus 1 equal to 2x. And x equal to u squared plus 1 over 2. Alright, now, so this answer comes from the u equals square root of 2x minus 1. So when I take a derivative of what I set u equal to up here, that's the equivalent of me take a derivative right here as well. Okay, derivative up here is the same thing as taking a derivative down here. So if I take a derivative of the u squared plus 1, let me do this on the side, okay? Alright, derivative in respect to u, or to x, excuse me, to x. Alright, u squared plus 1 over 2 can be split up looking as u squared over 2 plus u over 2. So remember now, this over 2 down here is a half, right? Times, bring down the exponent, bring the exponent down, the exponent subtract 1. Oh, I'm sorry, there's no u back here, there's just 1 over 2. Alright, and this part, derivative of constant becomes 0. So that means it's going to be half times 2u d sub u. So that would just be u du. Or u prime, du same as u prime. Alright, derivative in respect to u, or to x, excuse me. So that's just going to be 1 dx. Or just dx. So as you can see, the dx, let me use a highlighter, the dx right here becomes this. Okay. So now this whole bottom here becomes u, so that'll be 1 over u. So this problem becomes to the integral of 1 over u, because this whole bottom here is a u, and dx part becomes u times excuse me. Excuse me. This x right here, I'm sorry, this x right here is the u squared plus 1 over 2. And the dx part becomes u times u prime. Okay. Now, one of the reasons why I do that, because the u can cancel that. So the only thing left with to take the integral of, okay, is half times integral of u squared plus 1 du. I'll move my 2 to the outside, so this top is the only thing left. Okay. Now, I'm gonna show y'all something I never show y'all, because we've been evaluating in terms of x. Okay, so this 1 and 5, okay, is with the dx. So if I'm not gonna turn the u back to the x part, okay, then I cannot evaluate from 1 to 5. Right? It's a different set of numbers. So think about this. Okay, when x equal to 1, when x equal to 1, what does u equal to? So that will be, u will be square root of 2 times 1 minus 1. Okay, which my u will still be 1. So when I normally evaluate x at 5, what would it be if I were actually evaluate at u? So put a 5 right here. So that would be square root of 2 times 5 is 10. 10 minus 1 is 9. So that's u is equal to square root of 9, which is 3. So that means if I want to evaluate in terms of u, that will be evaluated from 1 to 3. Okay. So this is going to be half times, okay, bring down the u, excuse me, bring down the exponent to the front in the denominator, so that plus 1 that becomes 3. U to the third power plus u. Okay, and this part will be evaluated from 1 to 3. The reason I do this because it's easier. Okay, it's easier to evaluate definite integral using u sometimes. A little bit less step. So that will be half times 1/3 times 3 to the third power plus u is 3 minus 1/3 times 1 to the third power is still 1/3 plus 1. Okay, check it. If I substitute 1 here, 1 to the third is 1. 1 times 1/3 is still that 1/3. And put 1 right here for that u. So this becomes half times 27, 3 to the third 27, 1/3 27, 9. 9 plus 3 is 12. So that's 12 minus 4/3, which will give me this half will end up multiplying 32 over 3. 12 minus 4/3 is 32 over 3, which will, if I reduce them, that will be 16 over 3. That's my answer. So I went to a different route. Evaluate from the perspective of u instead of x. Okay. So different way to deal with these problems. Okay. Alright, I'm going to wrap it up this lecture video with a little bit of integration on natural log functions. Okay. So let u to be a differentiable function of x. Normally, as you can recall, I wrote this down before. The integral of 1 over x dx becomes natural log of absolute value of x plus c. Okay, so if I'm using u, that would be natural log of absolute value u plus c. Okay, so I want these problems to look like these pattern here. So nothing hard. Okay, I just want to show it to you. So if you look at this example, okay, I can actually factor out the half, or pull the half to the front. So that will give me half times the integral of 1 over x dx. Okay, so no problem. We've done similar problem like this before. So this is going to be half times the natural log of absolute value of x plus c. Okay, so what happens if my denominator gets a little bit more complicated, where I cannot simply factor anybody to the outside to make it look like a 1 over x? Then I can use u substitution. So I'm going to let my u to become the denominator here. Okay, so du will just be 4 dx. So that means my dx alone, this dx alone is actually du over 4. So that means I'm going to take an indefinite integral of 1 over u, so this whole bottom becomes u, dx becomes du over 4. Now I can factor out this 4 in the denominator and only take an integral of 1 over u du. So this part, the integral of it, becomes the natural log. So that will be natural log of absolute value of u plus c. And now I can bring my 4x plus minus 1 back for the u. So that will be 1/4 times natural log of absolute value of 4x minus 1 plus c. There you go. Alright. Alright, this last problem. See this x right here? Let's see if I need to do something with that x or not. So I'm going to let my whole bottom become u. And if I take a derivative, so in a way ahead of time I already know that if I take a derivative of the bottom, that will actually be 2x dx, and that x can help me with that x right there. So the x and dx part is right here. So to get the x dx by itself, I will divide both sides by 2. So that x times dx will become du over 2. So this is going to be the integral of 1 over u, times du over 2. So I can factor out the 2, factor out the half. Just take an integral of 1 over u du. So this part becomes a natural log of absolute value of u plus c, along with my half in the front. And now I can bring my x squared minus plus 1 back. So my final answer, half times absolute value, half times natural log of absolute value of x squared plus 1 and then plus c. Okay. Alright, so that will conclude our lecture video presentation for the U substitution, and this will also be our last video. So the Calculus 1 class, we will end it right here with this problem. Alright, thank you for watching. I hope you enjoyed this series. I do know that I sounded like monotone in many ways on the video recording, and I appreciate you bear with Mr. Chan here as well, and thank you so much for watching these videos.